Let's continue here with the life cycle of stars. The life on the main sequence for a star begins when the big ball of gas compresses and reaches a temperature of between 10 and 15 million degrees in its center. This allows this fusion reaction to start, the forming of deuterium from hydrogen that we looked at in detail in the last video. And the star lights up. So that begins its life on the main sequence. As I mentioned at the end of the previous video, the parameter that's the most important is the mass of the star at the, or the mass of this big ball of gas that forms the star. Its mass at the start of this process. We're going to talk about the various possibilities for mass, and so of a star, and the a convenient unit of measure is the mass of the sun. So we call that a solar mass, and the universal symbol for that is M, capital M for mass, with this circle with a dot in it, which I guess represents the sun. In any case, that's the symbol we always use for solar quantities, and M solar quantity is the mass. And just to give it a number, it's approximately 2 times 10 to the 30 kilograms. So 2 with 30 zeros after kilograms. But personally, I don't think that particular number is worth memorizing. It's just what's going to be more interesting is to consider the implications of the masses of various stars in terms expressed in terms of the solar mass. For instance, we're going to learn that stars more than 100 solar masses just don't form. As we'll explain soon. Okay, so the more massive a ball of gas, the higher the pressure will be in the center. Why? Because it's the pressure comes from the fact that it's squeezing in on itself due to the gravitational attraction. So the more mass there is, the higher the pressure. And you might, and this greater pressure leads to a greater temperature. Well, we've just said that you have to reach 10 million degrees at least in the center to start these fusion reactions. And so that implies that you need a critical amount of mass to reach high enough pressure that you have a high enough temperature that you start these nuclear reactions. So in other words, there's a minimum amount of mass that you need to form a star, and that number is about 7.5% of a solar mass, right? So, so Jupiter is a failed star, if you like. Its mass is about a 1/10%. So it would have had to have been 7 or 8 times bigger to have a high enough temperature in the center to start the reactions, the deuterium fusion reaction that starts the life as a star. On the other hand, if the mass of this big ball of gas that's trying to form a star, if it happens to be more than about 100 solar masses, then this proto-étoile, so this forming star, will be unstable, and it will just blow itself apart, and you won't be able to form a star. Well, this is interesting now because we have a range of masses that's required in order to have a star. If you don't have enough mass, then you can't reach the high enough temperature. If you have too much mass, more than 100 solar masses, then it gets too hot in the center and it blows itself up. So there's a nice physical reason for why there's a range of masses of main sequence stars that are slowly, gradually converting their hydrogen to helium. The lifespan of a star is strongly controlled by its mass. The more massive a star, that's at the starting point, the shorter the life. Yes, shorter. You didn't hear incorrectly, or I didn't say it wrongly. It's counterintuitive, but if you think about it, there's a good reason for it. It's because, well, we've explained it actually, but let's go through it again. So the greater the mass, the higher the pressure in the center. And the higher the pressure, the higher the temperature. And remember this fusion reaction, especially the first step of that proton-proton chain of joining two protons together to get a deuterium. That's a really unlikely event. It's a very slow process. And so if you can increase the temperature, you greatly can increase that probability of the two protons coming together. They want to repel because of the electrostatic repulsion of the two protons. So if a higher temperature means they're coming together faster, and they're more likely to join together, to fuse together to form the deuterium. So this rate of reaction is very sensitive to the temperature, which in turn is sensitive to the pressure, which is caused by the mass. So even though you have more hydrogen there to convert to helium, the greater the mass, the shorter the lifespan. It's a nonlinear effect. Now, we said that the sun has a lifespan of almost 10 billion years on the main sequence. It currently has an age of just over 4.5 billion years. And so that means it has a remaining lifespan just over 5 billion years, so that on the main sequence. The most massive stars, the really big, massive stars, only spend tens of millions of years on the main sequence. It might sound like a long time, but when we're in the scale of billions of years, millions of years is quite short. On the other end of the spectrum, the stars with a mass just less than 80% of the solar mass will have a lifespan longer than the age of the entire universe. Okay, let's look at the way astrophysicists organize data on stars in a little bit more detail. Let's by explaining the diagram of Hertzsprung-Russell, we have to understand two parameters. The first one is the luminosity of a star. So the luminosity of a star is a measure of how much energy is emitted by the star, and that will depend on the apparent brightness of the star when we observe it in our telescope, but it also depends on how far away the star is. So we have to measure its distance, for instance, with this parallax method that we described in the first part of this lecture. And then we can use that information to adjust the apparent brightness to calculate the actual luminosity of the star. So remember, the apparent brightness of a star falls off with the square of the distance from that star. So if we know the distance and the apparent brightness, we can calculate the luminosity, the actual rate at which energy is being given off by this star. We can also measure the surface temperature of the star. This is something that Sabine explained in the C'est pas sorcier video, using the spectrum of the star. So they look at the basically the intensity at different wavelengths. Wavelengths appear as different colors in the spectrum. But of course, it goes much beyond the visible, and it goes down into the infrared for the long wavelengths and up into the ultraviolet for the short wavelengths. And we can't see those with the naked eye, but they measure that with their telescopes, and they can determine the temperature of the photosphere, the light emitting part of the star. Okay, so we have these two variables that astrophysicists measure with their telescopes, and if we plot these on a diagram, we find that there's a strong relationship, and this was first discovered by Hertzsprung and Russell. And so the convention now is to plot the luminosity on the vertical axis and the temperature on the horizontal axis. And when you do that, you find that most stars, 4 out of 5, or 80% of the stars, fall on this sort of diagonal line, which we call the main sequence. This is the main sequence we've been referring to earlier. Well, let me show you the main sequence. So I got this from this European Space Observatory website, and so I'm crediting them. And so here we have a diagram of Hertzsprung and Russell with the luminosity on the vertical axes and the temperature of the surface of the star on the horizontal axis. It's a little bit confusing for several reasons. One is this blue end is actually the warmer end. So this line here, I'm not sure if you can read it, but you might have to download this PDF, which I will send to you. But it says here 30,000 degrees in Kelvin. And but this is a logarithmic scale. So this is 20,000, 10,000, 6,000. So now we have every 1,000, 9, 8, 7, 6,000, down to 3,000. So it's getting cooler as we move to the right. Which is and more red, which is all looks kind of counterintuitive, but anyways, that's the convention. And so the sun is around 6,000 degrees. So if we look up, we should find the sun, and there it is there. And if we look over here, we see that that's 1 unit. Well, what's the units of luminosity? It's in so the solar luminosity. So that is indeed the sun. The sun is on the main sequence. This is the main sequence here. And so that's what that's the feature that Hertzsprung and Russell discovered with this diagram. Most of the stars are on this main sequence, about 80% of them. Now you do have some that are down here and some red giants up here and etc. supergiants, but we'll describe at least the red giants later, but this is the main sequence. So we're saying that when a star most of the stars are on this main sequence, and as the composition of the star changes, its temperature and luminosity evolve, and the stars will migrate along the diagram of Hertzsprung and Russell. Okay, so I want to go into that in just a little bit more detail. So once when a star is born, when the dust cloud of hydrogen and helium and dust collapses on itself, and nuclear reactions start, then the fusion of hydrogen and helium to form eventually helium, when hydrogen fused to form helium, the star has been born, and at that point it will find itself on the whatever its surface temperature becomes, uh, and its luminosity becomes, it will be on the main sequence, in fact on the ZAMS line, the zero age main sequence line. But this will evolve during the life cycle of the star, for the following reason. As hydrogen is converted into helium in the central region of the star, it says here the nucleus of the star, but that's the term we use for the central region, is the nucleus. It has nothing to do with the nucleus of an atom or an ion. It's the central region of the star. And so as the central region of the star fills up with helium, it becomes denser. Why denser? Simply because helium is a heavier molecule than hydrogen. So it forms a denser gas. We're converting hydrogen into helium, and so the inside of the star becomes denser. But remember, the pressure is created by the gravity. So if you have a denser gas in there, you're going to increase the pressure, and this raises the temperature. We've just said that these fusion reactions happen slowly. They're limited by the probability of bringing the protons together. So if you can bring them together faster at a higher temperature, you're going to increase the rate of reaction. And so the luminosity of the star evolves, and it increases. The more hydrogen you fuse into helium in the central regions, the hotter the star becomes, and the greater the luminosity, the greater the energy output. So an implication of this is that the sun used to be weaker than it is today. For that reason, the luminosity of a star increases with time, and so it migrates upwards on the Hertzsprung-Russell diagram. It migrates upwards from this ZAMS zero-age main sequence line. It will, as it moves upwards, does it move to the left or the right? Well, unfortunately, the answer is a little bit complicated, and it depends on details that sort of go beyond what we're interested in. And in any case, this migration is rather subtle. I just wanted to emphasize that it doesn't just stay there. The output of luminosity of a star, and for instance, the sun, has evolved with time. If you're interested in biology, an implication is that or geology, the sun was weaker at earlier, in the time of the dinosaurs, for instance, and there's a certain climate paradox about why the Earth's climate is in fact warmer during these earlier time periods when the sun was weaker. Okay, that's the main sequence. The sun will spend about 10,000 years in this main sequence, fusing hydrogen to helium in its nucleus. What happens? What's going to happen at the end of 10,000 years? So about 5.2 billion years from now. Well, the inner part of the sun will use up, or equivalently a star of about one solar mass, will use up its hydrogen in the inner regions in about 10 billion years. So what happens then? Well, the nuclear fusion will stop there. We're shutting off that supply of energy. However, there's still hydrogen around in the outer layers, the layers that encircle the inner region, and this hydrogen will continue to fuse into helium. This results in the star inflating for these outer regions, the outer layers of the star, and in particular the photosphere, the outer layer where the light that reaches us is emitted. And so because it expands, these outer regions expand, the temperature tends to drop. And so this star is going to, or the sun in 5 billion years, will start to migrate to the right on the Hertzsprung-Russell diagram, migrating to the right to lower temperature. Unfortunately, I have to back up a lot. So these stars. So, for instance, the sun will migrate. This is 5 billion years from now. The sun will leave. It'll leave this main sequence, migrating to the right because its surface temperature is dropping, but migrating up because its luminosity is simultaneously increasing. It's increasing because the inner temperature is increasing, and also the area of the star, the surface area, is increasing, and therefore you have more surface to emit light from. But because the temperature is dropping near the surface, the color of the star will also evolve towards the red. The central region of the star will contract more, and this will liberate gravitational potential energy, emitting more radiation, and this radiation has pressure associated with it, which will cause the star to continue to expand in the outer regions, especially this photosphere, and its temperature will drop down to between 3 and 3,500 Kelvin. This is what we call a red giant. So let me go back to that. There we go. We're talking about this process of the sun evolving, 5 billion years from now, up into a red giant here with surface temperature between 3 and 4,000 degrees. I have another diagram that shows this here that allows us to. So here's the main sequence. It's a Hertzsprung-Russell diagram. So we have the magnitude of the luminosity. So it's here's the temperature on a log. Actually, that looks like a linear. Sorry, that's a linear scale. Yeah, going down. These are 2,000 degree temperature jumps. And the so this is the sun here, and at the end of its main sequence phase of life, it will, as I say, migrate to the right as its surface temperature drops, as the photosphere temperature drops, and it expands, and so it's giving off more and more radiation, and so it has a greater brightness and greater luminosity, and schematically it's shown here that it's become bigger and red. So it's a what we call a red giant. Okay, so let's do a summary now of this second lecture on stars. Remember, the resumes or the summaries are useful for you to sort of consolidate your knowledge, but also to see what I feel is the essential material that you should know. And if this doesn't make sense to you when you're reviewing for the exam, you should go back and reread the notes or listen to the lectures, the videos. So the what are stars? Stars are big balls of gas, ionized gas, and principally or mostly hydrogen and helium. We can measure their surface temperature and their luminosity being the amount of energy being liberated by or emitted from a star per unit time. And to calculate the distance to a star, at least for the stars that are close to us, we use a method called the parallax, in which we see the star appearing to move with respect to the much more distant stars during the 6-month period in which the sun has moved. The Earth has moved around the sun, and using geometry, you can calculate the distance to these stars. And I guess that's all we really have time to discuss in this class. There are many other methods for measuring distance to stars and galaxies used by astronomers and astrophysicists. And the parallax method is just the sort of the starting point that got going in the 19th century. When we make an important diagram for looking at stars and talking about the life cycle of a star is to place it on the Hertzsprung-Russell diagram. This is a diagram with the luminosity plotted on the vertical axis and the temperature plotted on the horizontal axis, but with this funny convention of higher temperature to the left and lower temperature to the right. But when you do that, you find that the most stars fall on this, what we call in the main sequence. Here's another example of a main Hertzsprung-Russell diagram with lots of stars on it, and most of them falling on this main sequence line. But we have some red giants up here, and I haven't talked about the white dwarfs here. Oops. Okay, some basic facts about stars. Stars shine. Where did that? As you know, but where does, so that implies that they're giving off energy, and so where does that energy come from? What's the source? It's nuclear reactions, and in particular, nuclear fusion reactions. And it's important that you understand that these are different than chemical reactions. When the star is first born, it's on the main sequence, and its nuclear reaction is the creation of helium from hydrogen. This happens in several steps, and we looked at the what one possible sequence that happens in the sun. I should have emphasized that different processes happen in different sized stars. But for a star like the sun, mostly we have that process that I was showing you, the proton-proton chain, in which the first step is to form a deuterium, which is a very slow process for a star like the sun. This is ultimately leads to helium. In other stars, you get different processes. You can fuse helium to generate carbon. In fact, stars are like big factories of the elements, right? They're nuclear fusion reactors that basically put the elements together for us. So any heavy elements like iron that we have here on Earth, that was at some point that iron was inside a star and was pieced to the nuclei of that iron was pieced together by nuclear reactions inside these stars. When stars start their life, they start on the main sequence on this, in particular on the ZAMS line, the zero age main sequence line. And that happens as soon as the central region of the star reaches between 10 and 15 million degrees. But as they fuse the hydrogen together to form helium, the star migrates on the Hertzsprung-Russell diagram away from the Zams line, and in fact it migrates up. Okay, let's finish with a little puzzle for you. Why is it more likely for life to form around a planetary system, or in a planet, in a planetary system, on a planet in a planetary system, around a star of mass similar to the solar mass, than it is for a corresponding planet orbiting around a much more massive star? Why would that be? What's the mass of the star got to do with it? It's not obvious unless you think of the duration of a life, of the life expectancy, or the time period on which the star is going to spend on the main sequence. Remember, it's much shorter for these more massive stars. They only spend a few tens of millions of years on the main sequence before they end their life. We'll talk about the end of their life in later later lectures, but these stars end their life. The more massive the star, counterintuitively, the more massive the star, the quicker it ends its life. Whereas a star like our sun will spend a good 10 billion years on the main sequence. There are stars with shorter, the less mass than the sun, and therefore much longer lifespans. Let's pause there.